condensate in a Bose-Einstein gas?
I will deal with a slightly different topic with respect to Oscar, who concentrated on charged particle reaction rates, and I guess that also Sandro yesterday focused on charged particle reaction rates, unless you go to the
most of the time, apart from the last few minutes.
Okay, so this is okay. During my talk, I will basically we will basically have a look to neutron capture rates, and this obviously interests the nucleosynthesis, the production of heavy elements heavier than iron, basically. And after a very short introduction, because I guess all of the people here are quite skilled on this topic, I will focus on two types of processes. That is the slow neutron capture process and the rapid neutron capture process. So having a look to the nuclide chart, and you see basically that the S process is proceeding very closely stick to the beta stability valley. During this process, the unstable isotopes freshly synthesized have enough time to decay back to their stable isobars before capturing another neutron. And in correspondence of closed shell configuration, in particular neutron magic nuclei, we have the so-called peaks of the S process. And this is here I just showed the first peak corresponding to the strontium, yttrium, and zirconium. The typical neutron density attained in the S process is around 10 to the 7 neutrons per cubic centimeter. On the other hand, if we have enough neutrons, that is the very high neutron densities larger than 10 to the 21, we have the so-called rapid neutron capture process. In this case, we have a series of neutron captures which basically proceed up to the drip line, and so very far from the beta stability valley. Also, in this case, there is a sort of a concentration of nuclei with neutron magic numbers, and as soon as the neutrons are no more available, you have the decay back to the stable isobars, and in such a way, you have the formation of the R process peak. And this explains you why in the solar distribution, we have a series of double peaks. On the other hand, we may not exclude that there are processes with intermediate the neutron densities, which are known in the literature as the EI process. In this case, the typical neutron density is about from 10 to the 14 to 10 to the 17. In this case, basically, you depart from the beta stability valley for some isotope, let's say from 3 to 7, 8, no more. And in this case, you have the nucleosynthesis, and the nucleosynthesis may also in some way bypass some neutron magic nucleus, and may proceed further in this direction. I will not really deal with the intermediate neutron process because we never focused on this processing in thermo. But, and there are, I suggest you to read these two papers, which are the most recent I found in the literature. But from the point of view of the from the experimental point of view, this process is extremely interesting because basically it requires the knowledge of neutron capture rates for unstable isotopes, which are close to the beta stability valley. So from the point of view of the experiments, they can be measured, perhaps not directly, but with, for instance, the so-called surrogate method, in which basically you study the DP reaction on And obviously you need a radioactive isotope beam in order to this process to occur. And also in this case, the most interesting reactions are those close to the neutron magic numbers. And for instance, one of the dreamers for this, one of the most important reactions to be studied in this process is the iodine 135, because it has the lowest neutron capture cross section in this region. So basically, it may let the process bypass this isotope or not, depending on its value. So going back to the S and the R process, we know that these processes occur in different stellar environments. In particular, the S process, the so-called main S process, that is the production of nuclei with a mass number larger than 90, occurs in asymptotic giant branch stars, while the production of the main contribution to the galactic chemical evolution of isotopes between iron and strontium come from the so-called weak S process, which is occurring in core helium burning and carbon shell burning phases of massive stars. On the other hand, the situation of the R process is even more difficult, because there are various possibilities to attain a full R process nucleosynthesis or a partial R process nucleosynthesis, depending on the availability of neutrons in your environment. So also in this case, there may be a full R process called main R process, which is able to synthesize isotope up to the actinides, or there are processes which are still classified as R process, but they are not able to develop the full nucleosynthesis up to the end of the R process path. In my presentation, I will basically concentrate on these two processes. And for this reason, I just introduce what is an AGB star. The asymptotic giant branch phase is attained by low and intermediate mass stars after the two main burning, that is the core hydrogen burning, the core helium burning. And as soon as you develop a carbon-oxygen partially degenerate core, you have that this core is surrounded by a helium burning shell and a hydrogen burning shell. This core is embedded in an extremely cool and expanded convective envelope. During this phase, basically, the luminosity is mainly provided by the hydrogen burning shell, but at a certain point, when the ashes of the hydrogen burning shell are deposited here, when here the condition to remove the degeneration is attained, you may have the activation of the triple alpha reaction, which occurs in a sort of develops a runaway, and these make this region to become fully convective. This is extremely important because it homogenizes all the products of the nucleosynthesis occurring in the interior of these stars. Then, as soon as the condition for a radiative helium burning are attained, all these the convection switched off, but all this region is expanding, and at a certain point, the hydrogen burning shell may switch off, and the convective envelope may penetrate in this region, which is extremely rich in carbon because you have the triple alpha reaction. But if you are able to, let's say, mix some of the protons here in this region, this reaction may occur and leading to the synthesis or the production of carbon-13, which basically will capture an alpha particle developing the S process. an additional contribution may come from the neon 22 plus alpha reaction, which is attained at larger temperatures for a shorter time. This is extremely important because it controls basically the so-called S-process branching. So when you have an isotope whose neutron capture rate is, let's say, or the same over or the beta decay, the S-process part may split into two different parts. And this is extremely important, as we will see soon. And then you have the dilution of the S process to products to the surface with the third dredge up. So this is a plot in which basically I compare the solar S process as a distribution of the so-called S-only isotopes, that is, isotopes which are shielded by stable isobars from the contribution of the R process, and with the observed solar distribution. And these numbers have been obtained by using AGB yields and massive stars yields from Marco and Sandro in Rome. And all the processes are taken into account from the birth of our galaxy. And then at the epoch of the formation of the sun, we have a certain isotopic distribution. And this distribution is compared to the solar one. So basically it means that if we obtain a value equal to 1, it means that the model is reproduced what it is observed in the sun. If we have a larger number, we are overproducing from the theoretical point of view. If we have a lower value, we are underproducing this isotope. And as you can see, considering that you have 12 orders of magnitude in the abundances of these elements, let's say that the agreement is pretty good, but obviously there are some striking points which even visually can be identified. And for this reason, I will concentrate on the two worst cases. Obviously, this is related to our models. It does not mean that this is a real problem, but perhaps it is a problem of us. But if I have to trust in my model, I would concentrate on these two isotopes from the nuclear point of view. And why? Let's start from gadolinium-154. In 2020, we proposed a measurement at the end of collaboration experiment at CERN, and we derived the new neutron capture rate. And we actually obtained a better agreement with the observation. So basically, at this point, shifted from here to here. However, still not exactly what we need. So if we have a look to the path of the S process around the gadolinium-154, you see gadolinium-154 is shielded by samarium-154 by any R process contribution. So it is extremely useful to test the robustness of S process calculation. So where can we improve the situation, or what can we study? So if you have a look here at uranium-153, you have a neutron capture. This is a stable isotope. So basically it captures a neutron and synthesizes europium-154. This isotope has a lifetime of 8 years, which is not that much, but it is exactly the period in which an S process branching may open. And as a matter of fact, you see that the main path basically proceeds through gadolinium, because you have the decay of the europium-154, but some of the europium-154 may capture a neutron and basically bypass the gadolinium. So the gadolinium production is determined by the branching at europium. So one very interesting candidate to be measured could be the European 154 N gamma from the experimental point of view. I just received this plot from Paresh, with whom I'm started a very recent collaboration, and he performed some Thales calculation on this neutron capture rate. And if we compare this new curve, which is the blue one, with the values available on the Cadonis database, which are the ones basically we use in our models, we see that there is a discrepancy of 30% in the region of interest, and it comes in the right direction, because basically it has a lower neutron capture rate. So it means that this isotope is less destroyed and it can decay to gadolinium, enhancing its abundance. So this one is an extremely interesting rate. So if we have a look to the other, let's say, beast for us, it is barium 134, which is definitely overproduced with respect to the other ones. We recently published a work with Simone Tajoli here in Trento, who derived the beta decay rate of this isotope, and we found that this rate with respect to the Takahashi-Yokoi tables, which are commonly used by stellar models, the rate is extremely different at the temperature of interest. And so basically, we obtain a reduction of this value from here almost to here. Again, not enough to reach our goal. So if we have a look to the, let's say, the path in this region, which is the neutron capture of cesium 133, which produces cesium 134, we see that cesium 134 has a lifetime of 2 years. Again, we are in that region where a branching in the S process may occur or not. And obviously, this branching determines the value of the barium 134. So, from our point of view, obviously, one interesting rate to be measured is the cesium 134 N gamma reaction. On the other hand, it is extremely important to have a very low uncertainty characterizing the barium 134. So these two rates are hopefully will be measured in the future and may solve or not this discrepancy currently affecting our models. And again, with the Paresh, we did he did some calculation, and curiously, all the theoretical calculations come in the right direction. So these models have been calculated without saying him anything. So I don't say him, I want this going up and this going down. He just calculated and sorry?
No bias.
No bias, exactly, no theoretical biases. This is not say that this is the truth, but at least we will see what we'll obtain by calculating new models. Another interesting region is the one closer to nickel. And in particular, I'm dealing with the neutron capture rate on nickel 64. Why? Because if we have a look to the distribution, the isotopic ratios, theoretical isotopic ratio we have in our models, and we compare them to isotopic ratio measured in presolar grains. Presolar grains are tiny dust particles found in the solar system, which preserve the nucleosynthesis of already extinct AGB stars evolved prior to the formation of the solar system. So basically, they really give us the possibility to study the nucleosynthesis occurred in another star. And these are extremely interesting because the precision of this measurement is astonishing, is at the order of 5%, while obviously spectroscopic measurements are, or let's say, an order of magnitude larger. And so the match of theoretical models with these ratios is extremely important. And as you can see, our latest model are in a, let's say, quite good agreement with this measured ratio, also for nickel. However, in this plot, I report nickel 61/58 and nickel 62/58. So you see, these ratios are in a good agreement. But if we have a look to the nickel 64/58, we see that there is a clear disagreement with respect to the measured values in laboratory. So the candidate to be analyzed here is nickel 64. Why? Because the available measurement for this isotope are normally around 30 kV. So basically, if we pass from the Cadonis 0.3 database to the most recent version, we see that the Maxwellian leveraged cross-section at 30 kV is more or less the same. You see 8 millibar and 7.7 millibar. But if we have a look to the profile published in those databases obtained with the same numbers available in the literature, we see that the extrapolation at low energy, in particular in the region of 8 kV, is extremely different, and no measurement have been performed in between the two, the release of the two databases. Simply, it has been chosen a different weight to the different measurement available in the literature. And so you see that in this case, we may pass from a value of 12 to a value of 27, which is more than a factor of 2. And obviously, this has a huge effect on the production of nickel 64 in our models. And this measurement has been proposed and TOF and will be performed hopefully next year. Another extremely interesting region is the one of selenium, krypton, and strontium. And in this case, I'm always dealing with unstable isotopes. In particular, the first one is the selenium-79. Selenium-79 is an unstable isotope whose neutron capture rate has never been directly measured. Well, actually, it has been recently measured in TOF, but the data are still not available. But this is extremely important for two reasons. The first one is that in low mass stars may determine the abundance of krypton 80, which is an S-only isotope, and in massive stars may determine how the S process proceed in this region. And for the weak S process, it is extremely important. Another interesting isotope is krypton 85, which is again an unstable isotope with a lifetime of 10 years. So we are always dealing with these isotopes with a lifetime between, let's say, some months and some years, which has never been measured directly. And this is important for two reasons. The first one, because it is determining how much of the S process passes to krypton 86, and then determine the ratios between 86 and 82, which is measured in grains. But most importantly, because krypton 86, it has the lowest neutron capture rate in this region, even lower than strontium 88. And this basically means that changing the ratio of, let's say, of the fluence passing in this direction or in this direction may largely determine which will be the abundance of strontium in your stars. And consider that strontium is the most important element of the first S-process peak, it means that the determination of the neutron capture rate of one single isotope may shape the whole distribution you obtain in your model. And it is extremely desired that someone in the future will measure this rate. And so, how much time?
9 minutes.
9 minutes. Okay, full. Good. I shift to the R process. For all concerned, the R process, the situation is slightly more, let's say, not confused, but let's say difficult, in the sense that when dealing with the R process, even the exact site of R process nucleosynthesis is still not clear, in the sense that R process may occur in different types of objects, and let's say the three most promising one are magnetorotational driven supernova, magnetars, and neutron star mergers. Obviously, in the last years, the focus has been on neutron star mergers because we had the possibility to study the kilonova-like curve following the gravitational event 170817, which has been triggered by the fusion of two neutron stars. All of these objects basically produce different R process distributions. And even within the same, let's say, scheme, in the same object, studying the same object may have different components, depending if we are looking at on the equatorial plane or on the polar plane, and so on. So basically, the number of parameters at play is high, and it is difficult to discriminate which model is better to reproduce the R process distribution. So the R process distribution reported here are simply the solar abundances from which you subtracted the S process abundances determined by the S process. So basically, it is an indirect way to study the R process. In any case, you see that different models may attain the production of different isotopes, and this will be further explained by Matteo in the afternoon. But basically, it is related to the availability of neutrons, of simply the availability of neutrons in your environment. So how can we improve the situation from the experimental point of view? In the sense, there are many uncertainties. Can we reduce the uncertainties in some way, even because the nuclear inputs adopted in these models are extremely various, in the sense that depending on the compilation, you can really obtain different results on the masses, on the beta decays, on the fission rates you use, and so on. So together with Diego Vescovi, we decided to perform a sensitivity study just focusing on neutron capture rates. So what we did, it has been to vary by a factor of 100 singularly neutron. It is not a Monte Carlo, but we singularly vary neutron capture rates. We concentrated on isotopes with an half-life larger than 1 second, and we explored 5 trajectories corresponding to the different ejecta from a neutron star merger. And and these are the results, which I will explain in a while. On the other hand, we also performed the effect of beta decay rates and beta delayed emission, neutron emissions in neutron star merger, and for what concerns this study, we verified that the most interesting isotopes are the one with a magic neutron number n equal to 82, in particular indium, tin, tellurium, and iodine. Going back to our sensitivity study, we used the simulation by Perego 2022, in which basically all the it has been determined the path that you can obtain on the, let's say, light elements in the final process distribution, and by this simulation we choose 5 trajectories representative of the different initial electron fractions, entropies, and expansion timescales, and these are the 5 let's say components we studied. And for all of these components, the time-dependent abundances have been obtained by convoluting the yields calculated with the Skynet code. The Skynet code it is a free available code, which basically allows you to calculate our process network distributions. And so doing this, what we obtain, sorry, this is just a sketch of the different reference distribution you can obtain by assuming different components. You see that, for instance, the dynamical ejector in the equatorial plane may attain a fuller process distribution, while the others not, and they basically they may attain the secondary process peak, or even just touch the first R process peak. And how did we proceed? We first varied a single neutron capture rate and then recompute the simulation. We varied them by a factor of 100. We calculated, we just restricted this study to those rates whose target nuclei reach an abundances of at least 10 to the minus 10, and at any time have an half-life, at any time of the baseline simulation, and half-life larger than 1 second, just to simplify the possibility to study them, because if we go to extremely short time scale isotopes, even from the experimental point of view, would be too much complicated. And we just focused on isotopes with Z larger than 20, because in Perego 2022 we noticed that their production is not influenced by neutron capture rates. And the goal is to identify rates that may have a large impact on the final process abundances, and obviously have a good chance to be measured in the future, because these are the reason for our choices here. And the other reason is to avoid performing a massive number of simulations. And these are the results. And you see that for each component, there are rates which may lead to appreciable variation, at least 1 order of magnitude. And obviously, this neutron capture rate, when are they important? Not at the beginning of the R process, because you have so many neutrons that you obtain you obtain an equilibrium situation in which neutron capture rates really do not matter. But as soon as the neutron fluence decreases, when the so-called freeze out occur, so when you have a few neutrons still available in your stellar environment, then basically it is the time when the distribution is shifting back to the beta stability valley. And at that time, having or not still a neutron available may modify the final distribution. Okay, and we also checked the effects on the light curves, in the sense that what happens on the light curve or the kilonova light curve if we vary this neutron capture rate, and these are the results we obtained for the various components. Obviously, the largest variation are obtained at late times because it is when, let's say, long lifetime isotope, long for the R process, are at play. Just to make okay, I will make you an example. And these are how we proceed. We evaluated both the absolute and the relative changes in the distributions, and we see that for what concerns the production of our process, the nuclei having the greatest influence are those located across the neutron closed shell regions, as you may easily understand why. And in particular, this is the cadmium, indium, tin region, tungsten for the third peak, and copper, zinc, gallium, selenium, and bromide for the first one. Then we did the same for the light curves, and what we see is that there are a few reaction rates that produce noticeable variations for IYA at relatively late times, larger than 10 days. And this is an example. If you produce strontium 89 in your ejecta, this is sensitive to the amount of bromine 89 and selenium 89, which in turn depend on the neutron capture rate on bromine 88 and selenium 88. So studying the neutron capture rate on this isotope, you determine the abundance of this one, which is able to inject energy later in the evolution of your kilonova light curve. This is the rationale of our approach. And obviously, this is very important because one of the most interesting topic related to neutron star merger is the determination of the kilonova light curve, which depends on many quantities, which are the numerical relativity simulation, which determine the physics of your merging, but also on the heating rates, which are basically depending on how much of each isotope you are producing, how much of the heat from this decay will be thermalized with the ejecta, and so the thermalization efficiency, and the opacities. The opacities, which will be the topic of the talk by this afternoon by Matteo, and he will explain you better what I'm meaning with this slide. So thank you.
Thanks, Sergio. Question? If you want, but
Okay, thank you. I have a warning and a question. So the warning is about these Thalys calculations, because you know Thalys is just a calculator. So whatever you put as an input, you get an output. Okay, so it's very easy to get like a factor to uncertainty because it just changed the optical potential, or because you know the optical potential that they're using, it's valid at 100 MeV, and then you make the calculation at 100 kV. So it's very risky to take the number as it is. Let's say it's very important to check what how accurate the physics is inside the code and which one you're choosing. So
Yeah. The ones I showed you are preliminary calculations, and so I guess that
So I didn't see any error bar, so that's why I got a bit scared.
Yeah,
You
okay.
easily get factor of 2, just
Okay.
easily.
Okay.
To my experience, let's say.
Okay.
And probably, like Carlos maybe knows the code better than me, or some of these theoretical.
It's interesting because since most of you don't know about it, and I always have said this so many times, probably you know, that once I sat with the festival 3 hours in a bus. You have heard this many times, right? But other people didn't. And he told me that there was this student called Hauser. He was a very bad student. 4 years. And he had to get his thesis. So what he did was on a rainy weekend, very often in Boston, he had nothing to do. He took the theory from Ewan Weisskopf, which is Hauser Feshbach. Hauser Feshbach is
Without speed.
Ewan Weisskopf is the Philip balance theory. Okay, and he put the angular momentum conservation, and then it worked much better than Ewan Weisskopf. And that's why we forgot about Ewan Weisskopf on the 30s, and we replaced with Hauser Feshbach. And Hauser Feshbach is a very bad theory. No, it's not a bad theory. It's the best we can do, but it has so many problems. You have inputs which we don't know, level densities, optical model for the potentials. So it's the best we can do, but it's very unpleasant. It's like our matrix. It's very unpleasant because the matrix is also a big thing. People say, "Oh, you talk with this Kuberman and Daniel Bay," and they say, "No, it's a theory. It's from Lane in the 50s, and people have played with it." But it's not. It's a fitting thing. It's like Hauser Feshbach. It's a fitting thing. You play with the parameters. So this Thalys thing is like you said, it's a black box. There are so many optical potentials there. And all these things are not, if you change them a little bit, you change a factor of 2. In factor of 2 is
If you are like,
if you are like, factor of 2 is a problem. So we have a conundrum in nuclear physics, how to do better. Some people like Stéphane Gorielli and others, they have tried, some French tried to improve and find a better theory, but we don't have much better. And I think Thalys is an effort from many people. We have to praise those guys because they put so much effort in these codes and it doesn't develop for many years. This is the best we can do, but it's not pleasant. And now I feel myself like Livio Strachey, talking.
The question is about this. You were mentioning about these calculation, sensitivity studies, and especially you said that this effect of the neutrons that you can have after the result. So in the calculation, did you? Is like this beta delayed neutron emission included in the studies?
Not in this one. Not
because
in this one.
if it is so sensitive to neutrons, then if you have
so if in the neutron in the calculation there are
beta delayed neutron emission, because if it is so sensitive, then that is like you can get neutrons.
Yeah. It should in the last version we used it should.
Okay.
Yeah.
Thank you.
Any other question?
Oscar.
It's a simple question. I don't know if you have the answer, but maybe someone else. Could you show the baryon 134 and gamma plots that you have shown? So so seems the thermal energy. No, the plot of the Maxwellian average. This one. So the dashed area. The ellipse area is the one where the reaction takes place in the S process. No.
For the cesium is the let's say the 30 kV region.
Yeah.
For the barium, I just focused on the 8 kV because you may destroy and produce it.
In any case, you are in this part of the plot where the rate, the Maxwellian average rise up.
Yeah.
So I'm wondering if this rise up is due to the presence of some resonance states in baryon 135. And in that case, the uncertainty is probably related with the uncertainty of the parameter of the state. That may be better understood, I think.
I don't know, perhaps the nuclear people may.
But usually when this kind, but this is not Alice, no? This
No,
is
he is saying that
This
the
is
curve,
canonical.
all the curves are going up.
Yeah. Yeah, like
Also, the scale is very much enhanced, so maybe it's just a way to show the data, so the result seems.
Sorry, what rotation is this? I don't.
È teorico, quindi quello che ci ha messo dentro basta mettere un esperimento teorico, quindi quello che ci ha messo dentro è quello che porta a questo.
No, the blue and the red one are with experimental values.
Ah, ok. Ah, ok.
The red one is, no, sorry, the blue is the new one. Oh, sorry, the blue is the new one. And the red is the old version of Cadonis. Sorry, I said I was not precise enough. I was focusing on the fact that passing from, in this case, passing from Cadonis to the new version, there is a 10% discrepancy, and that the theoretical calculation of Thales, it is exactly as the
question is within the Cadonis framework.
yeah.
The new value, let's say, is due to the improvement in some data, nuclear data.
No, it's just the way with which you are weighting the available data. And it is curious that the theoretical calculation is exactly as the Cadonis one value.
Aurora.
So, yesterday Alessandro was saying that somehow the outlier because the elements depends also on temperature. Where
Yes.
the reaction takes place. Did you try just to change a little this outlier to see what happens? Of course, you have to change probably all the elements.
But
Yes, probably.
for what concern the unstable ones with a clear temperature dependence, we already take into consideration with the theory available, in the sense that the Takahashi Yokoi provides a table as a function of temperature and electron density. And now recently, this has been improved with these new models by Simonucci and Tajoli, which is an order of magnitude more complex and which has more physics, and it changed this dependency. So it may also be that the decay rates are not are still not the real ones. Absolutely, that's true. That's true.
But I can add that actually up to 400 million degrees, the dependence on the temperature is negligible. It becomes extremely strong when you will go above 400 million degrees. Other questions, comments? Okay, let's thank Sergio again.